Alright, welcome back. Today we're talking about continuity and how to prove it by using limits. And we do this by the formal definition of continuity. And basically what we're doing, the easy way to think about continuity is a function is continuous if you can trace it and your pencil never has to leave the page to trace the full function. So there's no holes, no gaps, no asymptotes, anything like that. So we can use limits to prove this, and we're going to look at the different types of discontinuities that we could have and how to prove those. But the definition is right here. We're looking at a single point of the function, not the entire function. But we're looking at, the definition is that f of x is continuous at x equals a if the following three things happen. And all three of these next items have to be true. The first one is that f of a exists. So the value a that we're looking at exists. If I'm looking at a equals 2, I should be able to plug a 2 into the equation and I should get an output. That's the easiest one to prove. Number 2 is that the limit as x approaches a of f of x exists. What this really means is that there's a limit from the left and the right of a, and they are the same. Essentially what you really want to prove when available is that the limit as x approaches a from the right is equal to the limit as x approaches a from the left. And if you've shown those two, that statement is true, then you've actually shown that the limit as x approaches a exists. If they're not the same thing, then we're talking about a discontinuity. And the third thing is basically a combination of the first two rules, and that is that the value f of a is equal to the limit as x approaches a. So if they meet in the same, if they look like they're going to meet in the same place and the value is defined exactly where that place is, then these are equal and we have a continuous function. So what I'm going to do today is go over 4 different examples for you to really give you an idea how to prove these and what you're going to be doing. We're going to use those 3 criteria and let's get at it. First example, I'm going to draw it with a very awesome, up-to-date, detailed graph. Lord only knows what this represents, but I'm making it, so it's all good. So we have this function, we'll call it f, and I'm just going to label the point 2, 3. And down here, I'm going to label another point 2, negative 6. This is not to scale, obviously. And we're going to prove, obviously looking at that, again, the easy thing to think about is if I trace this with my pencil, eventually I'm going to have to jump down there just so I can go ahead and finish the function. So this is clearly not a continuous function. That's a jump discontinuity. So what's going to happen is we're going to go through our criteria. Step 1 is, by the way, we're going to prove continuity, or disprove continuity, I should say, at x equals 2, which we clearly know it's not. So it's going to fail one of these 3 things, if not all 3. So number 1, does f of a exist? F of 2 is this point right here. That's where it's defined. This is not f of 2, this is the value f of 2. So at x equals 2, f of 2 equals negative 6. So it succeeds on step 1. Now we're going to check step 2. Step 2 is checking the limit. Well, we check the limit as x approaches 2 from the left. And as we approach from the left, it appears that it's going to end up right there. We know it's not a defined point, but it still can be a limit. So that limit is 3. And we also check the limit as x approaches 2 from the right. And that's also going to be, from the right side, is going to be 3. This point has nothing to do with it. We're talking about limits, not values. Since these two are the same, you can therefore say that the limit as x approaches 2 of the function f of x is 3. It exists at 3. So it checks step 2. So we're looking pretty good right now, so it's got to fail this step. Step 3 is the value from number 1, f of 2, equals 6. And step 2, the limit as x approaches 2 is negative 3. 6 is not equal to negative 3. Okay, so therefore, not continuous at x equals 2. And that's what we're going to do every time. It's kind of a pain in the butt, but that's how it's going to play out. So we'll do another picture. They're easy to see on the pictures, usually a little bit more work working with the problem. So if we look at this, I'm just going to make a quick parabola, and I'm going to conveniently draw a hole right there. We'll call that function f. This time you'll notice I did not make another point, so the piecewise function I had here, that's not happening right here. There's no value at 2 that's defined. So this is going to be a pretty easy proof. So step 1, f of 2. You might think it's -3, but that is not a defined point. There are no defined points there, so f of 2 does not exist. So right there, we proved not continuous at x equals 2. That was nice and easy. Alright, and that's it. That's called that's a hole, we typically call it, but that's a removable discontinuity. Same thing. Another example. Okay, we're going to get more into an equation here. We're going to make a piecewise function. This is going to be 3x squared minus 2x. And the bottom, we're going to make it 2x plus 5 plus 5. Now you could graph these and look at it, but that's not our objective right now. Our objective, if we were graphing these, would be to look at and see at x equals 2, do these things end up in the same place? So you basically get the same y value. So step 1, f of 2. This is less than 2. This is greater than or equal to 2. So we're going to take this 2 from this function right here. So we're going to plug in a 2 for x in the bottom function. And we're just going to do the math. 2 times 2 is 4 plus 5 is 9. Square root of 9 is 3. Plus 5 is 8. So it exists. So we go to step 2. Now we're going to look at the limit. The limit as x approaches 2 from the left. So which of these is approaching 2 from the left? Well, these are numbers less than 2, so it's going to be this equation. So we're going to write 3, and we're going to plug in the 2. 3 times 2 squared minus 2 times 2. And you're going to do the math on that. That's going to be 4 times 3 is 12 minus 4 is 8. So right now that's looking pretty good with that. Whoops, I forgot to check the next step. So I also have to check limit as x approaches 2 from the right. And to do that, we're going to plug into this function. And we've already done that, and we already know that it is 8. So what we're having here is that the limit as x approaches 2 exists, and it's going to be 8. So that checks off step 2. Sorry about the mix-up there. I'll write this in pink as to not get confusing. Step 3, now we're just checking f of 2 equals 8, which is also equal to the limit as x approaches 2 of f of x. So we've checked off all 3 steps. You would say this is continuous at x equals 2. And that's how you do it. And I have one more example for you that I'll try to squeeze in here. It'll work. We'll get it. Last example, another piecewise. F of x equals, do some absolute values, negative 2x minus 1. Make that a little bit bigger. And a 2x minus 1. And these will be x is less than or equal to 2, x is greater than 2. Alright, so and we're obviously looking at x equals 2. So step 1, f of 2, this is the equal value right here. This is not, so we'll take from here. We are going to plug in a 2 into the top equation. And that's going to come out to be negative 4 minus 1 is negative 5. the absolute value of negative 5 equals 5. Bottom line, step 1 works. It succeeds. So now we check step 2. And I am going to move my work over here. Step 2, we're going to look at the limit from both directions. So as x approaches 2 from the left. Well, that would be these numbers here, which we actually just figured out. So we know that's going to be 5. But basically, you're just plugging into this equation, and just like we did, and we're getting 5. We're also going to check from the right. X approaches 2 plus. Okay, from the right, that's going to be numbers bigger than 2, which would be this side right here. So we're going to plug into the bottom equation, and we're going to get 2 times 2 minus 1. 2 times 2 is 4, minus 1 is 3. So what we have is a situation where this from the left is meeting at 5, and from the right we're going to a value of 3. So essentially we have some sort of situation where from the left it's approaching this spot, and from the right it's approaching this, which is obviously not continuous. These are not the graphs, I'm just freehand sketching. So we are going to say that the limit as x approaches 2 does not exist. And why is that? It's because 5 is not equal to 3. So we have failed step 2, so we say not continuous at x equals 2. And there you have it. This is going to cover many of the situations that you're going to run into. You just really want to remember here is that we can have a limit in a situation like that. It does not have to actually be defined at that point. All we need to have a limit is that from both directions it looks like it's going to the same point. It's not actually going to be on that point, but they're approaching the same exact value. So there's a limit there. There's a limit here from left to right. Just the defined value is there. All right, so that takes you through some examples. I hope this helps. It's not too bad, you just got to get used to the definition. And if you have any other questions, please feel free to let me know. Have a wonderful day, and I will see you soon.